When Bronsted-Lowry acids and bases react, it is actually just the transfer of a proton. So recall the Bronsted-Lowry definition of an acid is a proton donor. And remember, proton here is H+. And a base is a proton acceptor. So if you just stop and think about it, what's happening is the acid is donating or giving a proton, an H+, to the base. So we just have a transfer of H+, a proton. So we can look at a reaction, and in this class you do not have to be able to predict the product. So you'd actually be given a reaction just like it's shown here. And if we investigate it, and you have to look back and forth like between the reactants on the left-hand side of the arrow and the products on the right. So I see this I here, and I'm looking at what's happening. Remember, the only thing that should be changing is one of the reactants is going to be losing a proton, an H+, and the other one's going to be gaining it or accepting an H+. So when I look at this I here, I notice that it had a hydrogen and now or H+, and now it doesn't. So the hydrogen has gone to the water. And I'll change colors of the marker here, because again, if I investigate, just looking, the water, which is H2 over here, has gained an H+. So let's look at the definitions then. HI has given its hydrogen to the water. So HI is considered the acid in this reaction. And then water has accepted the H+ to become the H3O+ on the product side. So H2O, is the base. So in a Bronsted-Lowry definition, the acid and the base are each considered a part of the reactants. So one of them is an acid because it donated the H+, and the other one is the base because it accepted the H+. So let's look at the other side. So on the product side, we also label what's formed. So on the previous slide, we just labeled the reactants. One is the acid, the one that donated the proton, and the other is the base, the one that accepted the proton. But we also label what we call their partners, the conjugate base and the conjugate acid. So a conjugate base, this is a substance that forms. So these are things that are on the product side when the acid donates the H+. Okay, so in the previous problem, our acid was HI, and it went onto the other side, it made I-. So it formed the I-, so we would call that the conjugate, and I'm just abbreviating conjugate there, base. So I identified the acid as the HI and the I- as the conjugate base. Now in our previous problem on the other slide, we had identified water as the base. And so when you look, a conjugate acid is a substance that forms. So what did it form? And our water on the previous slide made H3O+. Okay, so that's what it forms. So a substance that forms when the base accepts H+. So water was the base, and when it accepted it, it became the H3O+, and this is called the conjugate acid. So let's see, we can predict the conjugate bases that an acid would form even if we don't have the reaction. So let's take a look. I have a couple examples here. And let's take a look. So the acid, that's what we're starting with. And this would be on the reactant side. And then its partner is on the product side. It's what the conjugate base is what the acid makes when it donates H+. So the acid, basically, to become the conjugate base, has to lose the proton. So if I have H2S, I'm going to lose one of these. So take away 1. So if I took away 1, I'm just imagining, then I would have an H left and an S, because I took away an H. And then when you take away a plus, you always leave a negative behind. Okay, so I'm removing, look up here, I'm removing H+. So let's try again. So if I have HSO4, and this is my acid here, and I take away an H, so just imagine, I'm donating the H, that goes away. So now I have SO4 left, and then when you take away, every time you take away a plus, you leave another negative. So if I have 1 negative right here, this guy would have 2 negatives left. So to figure out, if I only know that it's an acid, its conjugate base is the substance that would be left if you took away an H+. So you take away an H, and then you add another negative, because every time you take away a plus, you leave a negative behind. So let's look at water. So that if we're considering that as an acid, so we take away an H. So now in water it's a little weird. They don't write it HO, they write OH. And then there's no sign here. And I told you if you take away a plus, you have to leave a negative behind. And so you can see from the acids that I had written, I could predict the conjugate bases by taking away a hydrogen and adding a negative, because I'm taking away a positive. And every time you take away a positive, you leave a negative behind. Now this, so let's look at the bases. Let's see how that works. So when I look, it says a conjugate, here's on this side of the table, there's a base. So this is going to be on my reactant side of the equation. And the conjugate acid is going to be on the product side. I don't even have to have a reaction to be able to predict what it would form, because the definition says the conjugate acid is a substance that forms when the base accepts an H+. So what happens is a base is going to add an H+. So to figure out what it would do, I would look at my base formula, and there's an F there. So if I add an H, it would be HF. Now I'm also adding a positive, so this positive here would cancel out that negative, and so there would be no charge left over, so it would just be HF. Now if I add, let's do the next one, HCO3 negative. So I have H, I'm going to add an H to it, because that's what bases do, they accept. So now that becomes a 2. So I'd have H2, CO3. The only thing that's changing on any of these is the hydrogen. And then I'm adding a plus, I'm just imagining, so a plus cancels a negative, so then it would not have any charge. And then water, and notice I had water acting like an acid here, and now I have water acting like a base. Some substances can do both. They can accept or donate depending on what they're with. So I want to add an H+. So if I added an H, that would be 3. This has no charge here, so if I'm adding a plus, it's going to make it have a plus. Now what we call these groupings, these are called conjugate acid-base pairs. And I guess, and you're probably thinking, oh my goodness, these would be the same acid-base pair. these are things, what I want to show you, we're going to look at an equation when it's all together, is that you don't have to have an equation to know what the acid would make or what the base would make. If you have an acid that's a Bronsted-Lowry acid, we know it's going to donate a proton. So it's going to lose from its formula an H and a plus. If you have something that's a base, we know what it would look like on the other side because bases accept a proton. So its new formula on the product side would have an extra H and a plus. Now, these acid-base pairs, they have to happen together, right? Because it's transferring a proton. So let's look at how it would, how we would put it together for an equation. Now, let me remind you, in this class, you don't have to predict the product. So you're given something like this. But we can identify the conjugate acid-base pairs in this particular problem. So let's look at the first one. So remember, the only thing that's going to happen is a hydrogen's going to move. So I see that this HCOO3, that must go with this, right? Because the only difference is an H plus. And then with the water, that one must go with these. So those are my pairs. The only difference is one should lose a proton, an H plus, the other should gain. So when I look at these formulas, this one, the CHOO3, this one has lost or donated H plus. So that would be the acid. And what it makes is called the conjugate base. Now automatically this one then, the water, it gains an H plus, but it would have to be a base. And this would have to be the conjugate acid. So notice on both sides there's an acid and a base. And then when you look from the reactant to the product, the acid produces a base. So you can pause and try to figure out the next one, but I'm going to go ahead and I'm going to label the next one. So I see this P here, so I know the only thing that's changing is the proton, the H plus. So those two must go together. And then the OH, these two must go together. So those are the two pairs. So now I'm going to look which is the acid and which is the base. Well, I know acids donate proton and base accept it. So I look at this one and I'm comparing it to this one. And what's happened? This guy right here donated an H. So this is my acid, and the thing that it forms when it donates its H plus is the conjugate base. Now automatically this would have to be the base, but let's look at it. So it's OH minus here, and now it's H2O over here, so OH minus accepted it. So that's the base, and this is the conjugate acid. So that's how we label and identify in a reaction a Bronsted-Lowry acid and base, and then their partners or their acid-base pairs. Well,